Okay. Let me mute this. Okay, so let me go back to the PowerPoint. So basically, just as we said before, the strength of the bond here will affect the acidity, and the strength in this case, when it comes to oxyacids, is dependent on these two things I mentioned here: the electronegativity of Z and the oxidation state of Z, the atom that is bonded to oxygen. And these are just some examples of oxyacids. All right. So let's look at the electronegativity. Well, the oxidation number when it comes to the Z atom that is bonded to the oxygen. Actually, let's look at the electronegativity first. I'm sorry. So if you have the same atom, or I should say, the atom from the same group, in the same position in a general structure. So in this particular case here, this is chloric acid. You have, and this is bromic acid. And the only difference between them is that you have a chlorine here and a bromine here, right? So the question now becomes, how does that affect the acidity or the relative acidities of these two compounds? And it turns out that the acid strength is dependent on how electronegative the element is. The more electronegative the element, the stronger will be the acid, right? So chlorine is more electronegative than bromine, and therefore, as a result, the chloric acid will be a stronger acid compared to the bromic acid. And we see that trend in group 7. There's no such thing as HFO3, so we cannot have that comparison. But for the other 3 halogens, this would be the order of acidity. Basically, the chloric acid would be stronger than the bromic acid, which in turn would be stronger than the iodic acid. All right? So that's basically how the electronegativity affects the acidity. Now, remember, in order for us to observe that trend, of course, all the atoms that we're comparing in the different molecules must have the same oxidation number, all right? Because the oxidation number is also another factor that would affect the acidity of the acid, which is what we're going to look at next. So in the next slide, what happens if we have the same central atom Z, but they're bonded to different numbers of attached groups? And usually these attached groups are oxygen atoms. So for comparison, let's look at hypochlorous acid, which has this structure, compared to chlorous acid, which has this structure, compared to chloric acid, and then we have perchloric acid. So you'll notice as you go from one to the other, what's happening? The number of oxygen atoms around the chlorine here increases, right? This chlorine was only bonded to one oxygen atom, and then this oxygen is added to get from here to here, in the case of chlorous acid. And then down here, you have 2 oxygen atoms added, and then here you have 3 oxygen atoms added, right? So the question now becomes, how does the number of oxygens affect the acidity of the acid? And first thing I'm going to say is that the number of oxygens being attached to the chlorine results in the chlorine itself having a greater oxidation number. So as you can see here, the oxidation number of chlorine here is +1. In this case, it's +3. In this case, it's +5. In this case, it's +7, right? And what you'll find is that as the number of oxygen atoms increases, or as the oxidation number of the chlorine atom increases, the acidity increases. So therefore, for that reason, perchloric acid would be the strongest of these acids because it has the highest oxidation number, or the greater number of oxygen atoms surrounding it, followed by the chloric acid, followed by the chlorous acid, and then the hypochlorous acid, all right? And this is basically true right across the board. You could compare, for example, let me see if I have it here. No, I don't have it here. But you could compare, for example, hold on. You could compare, for example, sulfuric acid to sulfurous acid, right? What you'll find is that sulfuric acid will be a stronger acid compared to sulfurous for the same reason, right? Or if you compare nitric acid to nitrous acid, again, nitric acid would be a stronger acid compared to nitrous for the same reason. The greater the oxidation number of the atom, which is bonded to the oxygen, which is bonded to the hydrogen, the greater will be the acidity of the acid. All right, so that's a universal trend. Pretty much, I can't think of any exception to that. So that's basically how that works. Okay, let's talk about the acid-base properties of salts. Now, you may have learned in introductory chemistry or general chemistry of the neutralization reaction, right? Acid plus base gives you salt and water, right? And the general belief at that time, at that stage of your chemical education, would be that the salt that is produced will be neutral, because basically you'd expect that the acid and base will cancel out each other in terms of their properties, and the resulting products will be neutral. We know that water is neutral, but you'd probably expect that the salt is neutral. That is not true in all cases, and we're going to see where there are some cases where the salt is neutral, as in the first case here, but there are other cases where the salt would be either acidic or basic, and we can explain the reason why that is. So let's start off with a neutral salt. Basically, a neutral salt would be formed when you have a strong base reacting with a strong acid, right? So if you take, like, for example, hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base, the product of that reaction will be sodium chloride, and that salt, sodium chloride, will not have any effect on the aqueous environment, and as a result, the solution would be basic. Now, there's a couple of examples. One example of a strong base that would not give a neutral solution, and that is beryllium hydroxide. And we're going to get into the reason why that is so, right? But apart from beryllium hydroxide, pretty much all the hydroxides from group 1A and all the hydroxides from group 2A would be considered to be strong bases, excepting beryllium in this case. And therefore, beryllium hydroxide is a strong base, but it would not give a neutral solution when it reacts with hydrochloric acid. But all the other bases will give a neutral solution when it reacts with a strong acid. So as stated here, salts containing an alkaline metal or alkaline earth metal, excepting beryllium ions, and the conjugate base of a strong acid, such as chloride, bromide, nitrate, and so on, all right? So any salts fitting this particular description or criteria will end up forming a neutral solution when you add it to water. In other words, the pH is going to be 7. Now, okay, so here's the example of sodium chloride. So sodium chloride, when added to water, will dissociate to form sodium and chloride ions. The thing about it is that in the case of the sodium ions, whenever we try to find out whether or not a salt is acidic or basic, what we do is look at the interaction of the ions with water and see if it's possible or feasible. So in the case of water, if it were to interact with water, you're going to end up with sodium hydroxide and H+. But this reaction will not take place because sodium is a very stable ion in an aqueous solution. And if you think about it, it's impossible for sodium hydroxide and H+ to basically coexist in an aqueous environment. An acid-base reaction will take place. So therefore, as a result, no reaction will take place as far as the sodium ion is concerned. And the same is true for the chloride, in that you'd expect, if the chloride were to act as a base, it will react with water to form OH- and HCl. But again, this reaction will not take place because the chloride ion is very stable. And in any case, if these two were to be produced, they will immediately react to form back the chloride ion. So therefore, as far as the chloride ion is concerned, there's no reaction. So basically, the sodium ion and the chloride ion will not react with water, and therefore will have no effect on the pH of water, all right? And that's basically how we explain that, all right? Now, for the other situations, for basic solution, let me just erase what I just wrote on here. Let me erase down here. In the case of basic solutions, these are solutions formed from salts, which is formed from a strong base and a weak acid, all right? So basically, any salt that is formed from a strong base and a weak acid, when you add that salt to water, that solution becomes basic, right? So the example we're going to look at here is sodium acetate. And I just see here that there's an error. Let me correct that so that you have that. This H or this, where should I put it? It should not be here. All right. It's a minor thing, but important. Okay. So sodium acetate, right? Sodium acetate is a salt of a strong base and a weak acid, right? Now, what happens when sodium acetate dissolves in water? It forms sodium and acetate ion. Now, as we said before, as we described up here, the sodium ion will not interact with water. So therefore, the pH of the solution will not be affected by the sodium ion. However, in the case of the acetate ion, because it is a weak base, right, it will react with water to form the hydroxide ion and the acetic acid, right? And in fact, you're going to have a back and forth, right? You're going to have an equilibrium system being set up here, all right? So therefore, as a result of the formation of the hydroxide ion in this second reaction right here, the resulting solution is going to be basic, right? Because of course, the concentration of hydroxide ions, when elevated, will cause the solution to be basic, all right? So that's basically what happens in the case of a salt that is derived from a strong base and a weak acid. The solution resulting from that salt being added to water will be basic. Okay, then we get to the acid solutions. Now in this particular case, this particular type of solution is formed when a salt that is formed from a strong acid and weak base, all right? A good example of this would be ammonium chloride. Ammonium chloride, when added to water, gives you ammonium and chloride ions. The chloride ions, as we said earlier, when we were talking about the neutral salts, the chloride ions will have no effect on the pH of the solution. But the ammonium ion will, because what happens is that when the ammonium ion is in water, it will undergo dissociation to form ammonia and the hydrogen ion, all right? So as a result of the increase in the concentration of the hydrogen ion, that means that the pH of that solution will be low, which means that the solution will be acidic, all right? So that's what happens in the case of acid solutions. Okay, another little tidbit here that I need to add is that you can also have acid solutions formed from salts which have what we call a high charge density. What that means basically is that the ions, the metal ions from those salts are relatively small but have a high charge. Usually the charge is +2 and above, all right? So some examples of those salts are here. You have the aluminum ion, you have the chromium ion, and you have the aforementioned beryllium 2+ ion, right? These ions, when added to water, would make the solution acidic. Now, how does that work? We're going to use the aluminum ion as an example. When the aluminum ion goes into solution, it forms this complex ion right here, where you have the aluminum ion in the middle, and you have 6 water molecules surrounding it. And then what happens spontaneously is that one of the water molecules will lose a hydrogen ion. And the reason for that is because of the high charge density of the aluminum ions, which will pull electrons away from the hydrogen, which I'm going to show you in a diagram that is on the next slide, right? But basically what it shows you is that the aluminum ion, because of its high charge density, will release hydrogen ions into the solution, and then as a result, the solution will be acidic and will have a pH of below 7, all right? So this is the structure of the aluminum water complex. Central atom here is the aluminum, and it's surrounded by 6 water molecules in the form of an octahedron. And the way the proton or the hydrogen ion is lost is shown right here, right? So what happens is that another water molecule will come in and basically be attracted to this hydrogen. So therefore, this hydrogen will be pulled away and form the hydronium ion, and you'll be left with the rest of the structure here. And the hydronium ion being formed is what results in the acidity of the solution, right? And this is true not only for aluminum, also true for beryllium, true for chromium, and pretty much true for most of the transition metal ions. Any one of them, when you add it to water, will behave the same way and produce an acidic solution. All right? Okay, so let's summarize the different properties of acids, of acid-base, the acid-base properties of salt, right? the key thing you need to remember is how does the ions after dissociation interact with water, right? So as we said before, if the salt is formed from a strong base and a strong acid, so the cation is from the base, the anion is from the acid, then basically the pH will be 7 or approximately 7, right? And that's because there's no hydrolysis taking place, right? The ions that are formed will not interact with water to form any excess H plus or OH minus ions. Now, if you have a cation formed from a strong base and a weak acid, then the ion that will undergo hydrolysis will be the anion, right, which is basic. So therefore, as a result of the hydrolysis, hydroxide ions are formed, and therefore, as a result, the pH of the solution will be above 7. If the salt is formed from a weak base and a strong acid, then the ion that will undergo hydrolysis will be the cation, right? And as a result, the solution will be acidic because when the cation reacts with water, it produces hydrogen ions, and as a result, the pH of the solution will be less than 7. Now, here we get to a situation that we didn't discuss. What if the cation is from a weak base and the anion is from a weak acid, right? And here are some examples. Right? Well, the answer is that both the anions and cations will undergo hydrolysis. Now, the one that produces the greater amount of H plus or OH minus is what determines whether or not the resulting solution is acidic. So as stated here, if Kb is less than Ka, right? If Kb of the weak base is less than Ka of the weak acid, then the solution will be acidic and therefore the pH will be 7, or I should say less than 7. If Kb is equal to Ka, then the pH will be approximately 7. And if Kb is greater than Ka, that means that the resulting solution will be basic and therefore the pH will be above 7, all right? And then, as we said before, we talked about the small cations, high charge density cations. Those will produce, of course, an acidic solution, and therefore the resulting solution will have a pH of 7, all right? And that's basically how we predict the acidity of salts. So this is basically like a summary of what we just discussed. Kb greater than Ka, then the solution will be basic. If Kb is less than Ka, the solution is acidic. And if Kb is approximately equal to Ka, then that solution will be neutral. Okay, and this is just giving you some other compounds that are acidic. In other words, when added to water, form acids. Like carbon dioxide will form carbonic acid, and dinitrogen pentoxide, when added to water, will give nitric acid. So there are some oxides that are acidic, usually non-metallic oxides, where the non-metal part of it, or the non-oxygen part of it, has a relatively high oxidation state. Okay, now there's one more definition of an acid that we need to talk about. So just to remind you, we talked about the Bronsted-Lowry definition, which says that an acid is a substance which, when added to water, produces hydrogen ions, and a base is a substance which, when added to water, produces hydroxide ions, right? And then we got to the, no, that was the Arrhenius definition, I'm sorry. The Arrhenius definition is basically related to what happens when the acid is added to water, or base. If the acid is added to water and it produces hydrogen ions, then it's acidic. If it's added to, if a base is added to water and produces hydroxide ions, then that's basically tells you it's a base. So that's Arrhenius. Bronsted deals with the transfer of the hydrogen ion from one substance to another, right? So basically what Bronsted says is that an acid is a substance which donates protons to a base, and a base is a substance which donates protons to an acid, right? So in that definition, basically anything that does not have a hydrogen will not be considered to be an acid, right? So that's the Bronsted definition. Now we're going to get to a third definition, which is, so this is just reminding you of what the different definition is for acids, Arrhenius and Bronsted. The third definition we're going to look at is what is called the Lewis definition. And the Lewis definition is based on the ability of a substance to either donate or accept electron pairs, right? So basically, according to the Lewis definition, a Lewis acid is a substance that can accept a pair of electrons, and a base is a substance that can donate a pair of electrons, all right? And just to give you a simple example, H plus plus OH minus. Now, according to the Lewis definition, right, what will happen in this case, the hydroxide ion will donate a pair of electrons to the hydrogen ion, right? So therefore, according to the Lewis definition, and this forms water, according to the Lewis definition, the hydrogen ion will be the acid because it accepts a pair of electrons, and a base is, according to Lewis, a substance which donates a pair of electrons, so therefore the hydroxide ions would be the base, right? So that's basically the definition of an acid and a base according to Lewis. Here's another example. If you add H plus to ammonia, again, you're going to have an electron pair here, which will be donated to the acid to form ammonium, right? So therefore, as a result, the H plus ion is considered to be the acid because it accepts an electron pair from the ammonia, and ammonia is considered to be a base because it donates a pair of electrons to the H plus, right? And the result will be the formation of the ammonium ion, all right? Now, the key difference between the Lewis definition and the Bronsted definition is that it's not even necessary for there to be a proton involved in order for it to be considered to be an acid-base reaction. And here's an example of that. The reaction between boron trifluoride and ammonia, right? In this particular case, the ammonia is considered to be the base because it donates an electron pair to the boron. Now, you might be wondering, why does a boron accept an electron pair? Because it's not charged. Well, the answer is that even though the boron is not charged, it is still considered to be electron deficient. And the reason why it's considered to be electron deficient is because the boron atom has only 6 electrons on its outer shell, right? Remember, for stability, it needs 8, right? So even though there's no charge on the atom itself, the atom itself is still considered to be electron deficient and therefore will accept electrons from anybody, right? So what happens is that this pair of electrons will be donated to the boron. As a result, based on the Lewis definition, the boron trifluoride will be considered to be acidic and the ammonia will be considered to be basic, right? And please note, in this particular example, there's no transfer of hydrogen from one atom to or from one molecule to another, right? So therefore, according to the Bronsted definition, this would not be an acid-base reaction. But according to Lewis, this would be an acid-base reaction because this is based on the donation of electrons from one atom, from one molecule to another atom of the other molecule, right? So as stated here, there are no protons being donated or accepted, so therefore this would not be considered to be an acid-base reaction according to Bronsted, but it is an acid-base reaction according to Lewis. And finally, some applications of acid-base reactions in the manufacture of certain antacid preparations, right? Nearly all, if not all of the antacids that you find at any pharmacy contain some form of base, all right? And that's because antacids basically neutralizes the acid, the excess acid that is produced in the stomach in the condition known as heartburn. Has nothing to do with the heart, it's just that, you know, the acid contents of the stomach finds its way up into what do you call it, the alimentary canal, and I think they call that acid reflux, right? So basically, you know, there are several preparations that have been manufactured, and if you look at the composition on each of these, you have at least something basic involved. So an example of this would be milk of magnesia, which contains magnesium hydroxide, right? And of course, it reacts with hydrochloric acid according to the equation that you see there, all right? That's basically it for this chapter. So, I think we have completed, or you should be able to complete all the questions in the assignment. Or if you have any questions about any of the assignment questions, I think now would be a good time for you to ask. Let me see if I can bring up the assignment here. This is assignment number 4. Oh no, not that. Right. I don't remember the last question I did. you can tell me. Or you can tell me what, if you have what problem you like me to look at. What? Let me see here. Okay, you know what? If you, unless you guys have any idea of what you want me to do, I could start by looking at number 11. All right? Okay, so number 11 says calculate the pH of the following solution. And the first one is a 0.20 m hypochlorous acid solution, and it gives you the Ka for the hypochlorous acid. So fortunately for us, we don't have to look for it. Remember, there's a table which has a list of Ka and Kb values for acids and bases, which will be available to you during your test, all right? Okay, so first thing I would do is construct, of course, an ice table. Okay, so I'm just going to write a dissociation here. We give H plus ClO minus, and the initial concentrations would be for the HClO 0.20. This will be 0, this will be 0. So if you remember, I think we did at least one example of this type in lecture. Remember we said that we don't know what the change is, but because we know it's a weak acid, we know that some of this will react. So we're going to say that the change, as far as that is concerned, is X, which means that the change here will be plus X and plus X. So at equilibrium, you're going to have 0.20 minus X, and here you're going to have X, and here you're going to have X. So now we can write down the Ka value, or the Ka expression for this equilibrium, which is concentration of H plus times the concentration of ClO minus, and then divided by the concentration of HClO. And then we put in these terms into this equation, X squared over 0.20 minus X. And then if you recall, we talk about making an assumption. We assume that what? X is much less than 0.20. So that 0.20 minus X is approximately 0.20. So that simplifies this to X squared over 0.20, right? And then we solve for X. So X is going to be equal to the square root of Ka times 0.20. And Ka is equal to 3.2 times 10 to the minus 8 times 0.20. And then we do our number crunching, 3.2 times 10 to the minus 8 times 0.2. And then I find the square root. And please correct me if I'm wrong, but the answer I got is 8.0 times 10 to the minus 5. All right? And then what do we do next, if you remember? We have to calculate, we have to check to make sure that the approximation we made is valid. So how do we check that? We find the what? Yeah.
Under the square root, is that K?
Ka.
Ka times 0.020 or?
0.20.
I mean, yeah, 0.20, or is it KX 0.20?
No, Ka times 0.20, yeah. Okay, so what do we do at this stage in order to check or test to make sure that our assumption is valid? We do what? Find what? Percent dissociation, very good. Miss, or should I say Senorita Luna. Okay, so how do we find the percent dissociation? In this case.
Do 8.0 times 10.
8.0 times 10 to the minus 5 divided by?
The 0.20.
0.20, exactly. Multiplied by 100%. And I can tell this will be less than 5%, which is a criteria that we use, right? 8 times 10 to the minus 5 divided by 0.2. So that would be 4 times 100, almost for that. So that would be 0.040%, which is obviously less than 5%. So that means that we can basically go with this as being equal to the concentration of H plus. So how do we find the pH? Now that we have the concentration of H plus, pH is equal to what? Minus log of?
8.0.
Exactly, 8.0 times 10 to the minus 5. So let's see what that gives. 8.0 log, oh no, 8.0 times 10 to the minus 5 log and then minus, okay. So my answer is 4.10 because you have to round off to 2 decimal places because this is into 2 sig figs. So that's the answer. Again, please check to make sure I'm doing the right thing because I could be wrong. Okay, any questions about this one? Yes, ma'am.
So far you have X is less.
Well, it is 2 less than sign. I don't know if you have met that in math before. It means much less than.
How much less?
Right.
And then the one on the other side, is it greater than?
Where?
Yeah.
No, you mean this?
Yeah.
No, that's approximately equal to. So
Oh,
what I'm saying here is that X is so small compared to 0.20,
okay,
such that 0.20 minus X is approximately 0.20.
okay, got it.
See what I'm saying?
Yeah.
Yeah. Okay, any other questions? Any other questions? All right, is it okay for me to clear this? Going once, going twice. All right, let me go ahead and clear all this and scroll down. Okay, now the next one, you're asking for the same thing for this solution right here, 0.055 M sodium cyanide solution. Now, this is a bit different because we're starting from a salt, and we just talked about the fact that some salts are neutral, some salts are acidic, some salts are basic, right? It depends on the type of salt, right? If the salt is formed from a strong base and weak acid, then that would be a basic solution. If the salt is formed from a strong acid and weak base, then that would be an acidic solution. Now, in this particular case, it's sodium cyanide. So they gave you the Ka for hydrogen cyanide. That should give you a hint as to the type of salt this is in terms of the type of solution we'll form. Because the cyanide comes from a weak acid. The Ka is 4.9 times 10 to the minus 10, which is a small number. That tells you that the hydrogen cyanide is a weak acid. So basically this is a weak, this is the salt of the weak acid, and the sodium we already know is the cation formed from a strong base. So what we need to do is examine the type of reactions that will be taking place when you add the sodium cyanide to water. So NaCN added to water will give you what? Dissociation. Na plus Cn minus. So the question now becomes, what happens after these two dissociate? How will they interact with water? We already know that sodium will not interact with water, but the cyanide itself will interact with water as a base, according to this equation right here. HCN plus OH minus, right? So that's basically how that happens, and therefore we can set up an ice table. Initially, the molarity of the cyanide ion would be 0.055. We know that to be so because that was the molarity here. And because of the 1-to-1 ratio between the sodium cyanide and the cyanide itself, the molarity of that solution initially would be 0.055, right? Okay, so that's the cyanide. As far as the HCN is concerned, that would be 0. And as far as the OH minus is concerned, that would be 0. Change, minus X plus X plus X, right? So at equilibrium, you're going to have 0.055 minus X. Here you're going to have X. Here you're going to have X, right? Now, we can write down the Kb expression because remember, we're dealing with a base. right? So therefore, the KB expression would be the concentration of HCN times the concentration of OH minus divided by the concentration of CN minus. So this is based on this equilibrium equation right here, right? So all we have to do is put in these terms into this equation, and this becomes x squared over 0.055 minus x, right? And that will be equal to KB. Now, two things we have to look at here. So this is KB. The first thing is what we saw earlier, what we did earlier. We assume that x is so small. So we assume x is much smaller than 0.055, so that 0.055 minus x is approximately equal to 0.055. All right? Okay, so basically this simplifies this to x squared over 0.055, which means that x, continue down here, would be equal to the square root of KB multiplied by 0.055. And we are given a KB here. Oh no, we're given a KA. Okay, here's where the second issue comes up. We need KB here, but you're given KA. And there's an equation which relates KB to KA. Can anybody tell me or remind us of what that expression is? There's a relationship between KB and KA. What's that relationship? Relationship between Ka for an acid and Kb for its conjugate base. And they gave us the Ka for the weak acid. What's the relationship between Ka and Kb? And by the way, you guys out there in Zoom, you can join in as well if you think you know what the answer is. What's the relationship between Ka for a weak acid and Kb for its conjugate base?
KW over KB.
Ka is equal to what?
KW over
Kw divided by Kb, exactly. Right? So basically, I'm going to put here square root of K. Well, this is Kb they're asking for. So we can rearrange this to get Kb is equal to Kw over Ka, all right? So we can put here Kw divided by Ka multiplied by 0.055. Now Kw is a constant, which is 1.0 times 10 to the minus 14 multiplied by 0.055 divided by the Ka, which is given as 4.9 times 10 to the minus 10, right? So this is what's going to give us x. So 1 times 10 to the minus 14 times 0.055 divided by 4.9 times 10 to the minus 10. And and then square root, can't forget that. According to my calculation, this works out to be equal to I need to run this out to 2 sig figs. So this will be 1.1 times 10 to the minus 3. Again, please check to make sure I'm doing the right thing, but this is what I got, right? So once we get that, then like we did before, we need to find the percent dissociation. Percent dissociation is what? 1.1 times 10 to the minus 3 m divided by the initial concentration, which is 0.055 m times 100%. So let's see what that gives. 1.1 times 10 to the minus 3 divided by 0.055 times, what am I doing? Times, well, 0.02 times 1. So I got 2%, which is obviously less than 5%, right? So therefore, we can say that the concentration of hydronium is 1.1 times 10 to the minus 3. So that means that the pH is equal to minus log of 1.1 times 10 to the minus 3. Let me see what that gets. 1.1 times 10 to the minus 3, and then do the log, negative. Okay, so I have to round this out to 2 decimal places, so I got 2.96. All right? Any questions about this one? Mhm.
For the KB, it's KB equals. What's the thing in the,
Here,
on the top, yeah?
KW, which is a constant. KW is equal to 1.0 times 10 to the minus 14. That is also in the tables that I have posted in Canvas. Right. Okay, any other questions? Any other questions? Any other questions? Okay, so, is it okay for me to clear this? Going once? Going twice? All right, let's see what's next. Okay, let's see if you can do this one based on what we have done before. Again, the task is to find a pH, but this time it's a solution of 0.35 m ammonium chloride. So what's the first step in this process? Excuse me. First step would be, okay, but what would be the equation? And let me just say that there are two equations, because there's one equation for the dissociation of the salt, and then there's another equation for the hydrolyzation or the reaction between water and the ions. All right? So what would be the first equation? What would be the equation for the dissociation of ammonium chloride? NH4Cl, oops, hold on. NH4Cl will produce what when added to water? Dissociation. When it dissociates, what's formed? I'm sorry?
NH4 plus Cl.
NH4 plus Cl minus. All right? So the next step is, how will water interact with each of these ions? And if you recall, we said that the chloride ion is very stable, right? So therefore, there'll be no interaction between the chloride and the water. The ammonium ion, on the other hand, will undergo a reaction with water. What would be the products of that reaction? And let me give you a hint. It's going to act as an acid. It's going to act as a Bronsted acid. What will a Bronsted acid do? It will donate protons, right? It will donate, so the ammonium will donate a proton to the water, right? So what will be the result of that proton transfer? NH3 plus
H plus.
H. You said H plus? Okay, that's true too, but since we have included water here, that would be H0 plus. Because the proton will be donated to the water, all right? Okay, so now we can set up our ice table, right? Initially, the concentration of ammonium would be 0.35, right? And the initial concentration of ammonia and H0 plus would be 0. And then the change would be minus X here, plus X here, plus X here. So therefore, at equilibrium, you're gonna have 0.35 minus X. Here you're gonna have X, here you're gonna have X, right? So what we can do right now is write down the equation for the dissociation, the dissociation constant equation, which is Ka is equal to the concentration of NH3 times the concentration of H0 plus, all divided by the concentration of NH4 plus, right? And then we put in the terms, we're gonna end up with X squared over 0.35 minus X, and that would be equal to Ka, right? Now, what's the next step? You should be able to tell me what the next step is. You assume that X is much smaller than 0.35, so that 0.35 minus X is approximately equal to 0.35. So this simplifies to X squared over 0.35, which means that X is equal to the square root of Ka times 0.35. But guess what? We're not given the Ka, we're given the Kb for ammonia. What we need is a Ka for the ammonia. So how would you find the Ka? Ka will be equal to what?
W over KB.
Kw over Kb, yeah. So we're gonna put Kw here over Kb, multiplied by 0.35. And then we put the numbers. So Kw again is 1.0 times 10 to the minus 14. Divided by Kb, which is 1.8 times 10 to the minus 5. Times 0.35. So let's see what that gives. 1 times 10 to 1. Multiplied by 0.35. Divided by 1.8 times 10 to the minus 5. And find the square root of that. And according to my calculations, this will be equal to 1.4. Roll it off to 268. 1.4 times 10 to the minus 5, right? So this will be equal to the concentration of H3O plus. So all we have to do now is find what? The pH, right? So the pH is minus log of 1.4 times 10 to the minus 5. Put the minus sign in front of that, and according to my calculations, this works out to be equal to 4.85. 4.85. And that would be how you do that. Any questions?
Do the percent.
Oh, right. It's less than 5%, I can't tell, but yeah, you're right. You should do the percent. Let me do that. So percent dissociation, I'm just going to squeeze it right here. That would be equal to 1.4 times 10 to the minus 5 divided by 0.35 m times 100%. And if you do that, 1.4 times 10 to the minus 5 divided by 0.35 times 100. According to my calculation, that's 4 times 10 to the minus 3%. 4 times 10 to the minus 3%, which is obviously less than 5%. So therefore, everything else that follows is correct. Okay, any questions about this one? Or any other questions about this one? Nope. All right, let me assume I can clear this. And let me scroll down. Okay, D, let's see what you can come up with for this one here. What's the first thing you would do in this case?
Dissociation.
Okay, so in the case of ammonium hydroxide, which is a base, there's only one equation that it's not a salt. So the only equation that you'll be concerned with is NH4OH in equilibrium with NH4 plus OH minus. So initially would be 0.50 m for the ammonium hydroxide, 0 and 0 here. We change on the minus X like we did before, plus X here, and therefore at equilibrium, you're gonna have 0.50 minus X, Kb is going to be equal to the concentration of NH4 plus times the concentration of OH minus divided by concentration of NH4 OH And then we put in the different terms, x times x, or let me just say x squared, save myself the trouble. X squared over 0.50 minus x, and then we do the approximation of 0.50 minus x is approximately 0.50. So this simplifies to x squared over 0.50. So therefore, x would be equal to the square root of 0.50 times kb, which is equal to 0.50 times the kb, which is given here, 1.8 times 10 to the minus 5. So let's do that calculation, 0.5 times 1.8 times 10 to the minus 5. And then find the square root of that. And according to my calculation, this works out to be equal to 3.0 times 10 to the minus 3 m, which would be equal to the concentration of OH minus. So the next step is to find the percent dissociation. And that would be equal to 3.0 times 10 to the minus 3 divided by 0.50 m times 100%. Times 10 to the minus 3 divided by 0.5 times 100%. And according to my calculation, this works out to be equal to 0.6. So that means that we can find the pH. So how do we find the pH? We now have the pH, we now have the concentration of OH minus. So how would you go about finding the pH? Find the pH, right. So the pOH would be minus log of 3.0 times 10 to the minus 3. And then, let me see here. pOH, we need to find the pOH first before we can find the pH, because what we have so far is the concentration of OH minus. So what we do is find the pOH first, which is minus log of 3.0 times 10 to the minus 3. Find the minus log of that, and according to my calculation, this works out to be equal to 2.52, and then the pH will be equal to 14.00 minus 2.52. And according to my calculation, that will work out to be equal to 11.48. And that's what you do then. All right, any questions about this one? Any questions? Okay, I take it I can clear this. Can I clear this? Oh. Here?
Yeah.
Okay, so this is another equation. I'm not sure if this is in the table, but the relationship between pH and pOH is this right here. Is equal to 14.00. All right. I don't remember if this is in the tables that I've posted in Canvas, but just in case it's not there, that's a relationship. Right. So once you know one, you can calculate the other easily. All right. Once you know pOH, you can calculate the pH and vice versa. All right. Any other questions about it? Any other questions? Okay. Let me see here. Oh no, should have done that. First. Okay. Let's look at this one, number 12. What is the pH of a solution of a 0.25 m weak acid that is 2.2 ionized? And it gives you this hypothetical acid dissociating. Well, this one is actually rather easy because whatever the amount of acid that dissociates here, the concentration of H plus would be the same. And they said that the acid is 2.2% ionized. So what I would find out is the concentration of H plus at equilibrium. at equilibrium, the concentration of H plus would simply be equal to 2.2 over 100 multiplied by 0.25. Yeah. So let's see what I get. So according to my calculation, this works out to be equal to 5.5 times 10 to the minus 3 M, right? So that's it, pretty much, because all you have to do is find a pH. That's what the question is asking for. Minus log of 5.5 times 10 to the minus 3. And that's it. So let me do that. Okay, so according to my calculation, the answer is 2.2 decimal place, 2.26. And that's it. So nothing much to do here to solve this problem. All right. Any questions? Any questions? Okay. Oh, shoot, why did I keep doing that? All right, scrolling down. Okay, I think this is probably going to be our last question. In fact, hold on,
You
let's
said
see.
not to do that.
Yeah.
one.
Oh, that's a repeat. I remember, right? It's a repeat. Thank you for reminding me. Okay. All right. I don't think I'll be able to complete this one in time, so I'm going to stop here. But you can try this question on your own. Let me see. 15, 16. Yeah, try the rest of them. I would understand, especially for number 16, you might have some difficulty with it. And I'm more than willing to help you with that one next class. So, but you can try it on your own and see what you can make of it, all right? All right, I'm going to stop here for today. And we'll continue on Wednesday.
Do that. Okay.